Hello, my name is Peter J. Tucker, and this is for Communication Systems EE401 Project number 2, Software-Defined Acoustic Modem. A script was built to be able to use the ASCII TX functions and ASCII RX functions that I also created. The ASCII TX function uses a sampling frequency and a carrier frequency, as well as a key value and a text-in message. What it does is it converts the text-in message from ASCII to bits, and then modulates the signal and samples it. Well, it samples it before it modulates it, and then it's saved to a WAV file. The WAV file is then saved to my phone, and then I will play back that message, and I'll use MATLAB to record the message back. I'll show that part here. And I'll record it back, and then I'm going to use the ASCII RX receive function to demodulate the signal, break it down through the frames, and recover the message bits, and then reconvert those bits back into the original message that we sent. The sampling frequency I used was 44.1 kilohertz. Most sampling frequencies for audio devices in recording and playback tend to be 44.1 kilohertz or 48 kilohertz, so I just figured I'd go for 44.1. The ASCII symbols are typically 7 bits, but when we encode them, we're encoding them as 8. The key I used is right here. It's a 0, 1, 1, 1, 1, 0. I think I said that right. It's six numbers, all binary. And I chose something that was this size. I could have gone with something larger, and that probably would have made some things in some ways a little bit easier. But the amount of recursiveness that has to go through the process takes a lot longer. With a key value of 6, I can do a modulus in my receiver function, which I've done, that looks for sets of 8. So it searches between where it thinks it finds key points and makes sure that there's an amount of characters that are divisible by 8, or an amount of bits that are divisible by 8, to make sure that it's the correct key. It's not a false positive key. So it chose this number for the key because there's typically not a lot of ASCII characters that have 4 ones in them, either at the beginning or the end. There's a couple that are not used as well. I figured that would make it a lot easier to not get false positives. And then I've also repeated the text in, which is my name, 9 times. Our samples per symbol are 90, and the waveform that it gets saved to is this test wave 1, or test1 .wav file. And then when we save the new recording, we're going to be saving it as a file name of test2.wav to separate the two out. I should also mention that I've set the carrier frequency to 2000 hertz. I found that with working with some of the with trying to work with my phone, which has been really difficult to try to get a clear signal out of it. Working with something that's a little bit lower was better than working with something with higher frequency. And the frequency at 2000 still gives us enough of a buffer, so when our baud rate comes back is 490, because it's going to be pushing on both sides of where that carrier frequency is. It's going to be the carrier frequency plus the baud rate of 490. And then the carrier frequency minus that baud rate of 490 for our full double-sided bandwidth there. So we wanted to make sure there was something that was high enough to be able to get us outside of that range, so we're not hanging off into 0 and then having crosstalk with the negative side of the frequencies, as well as also still staying under enough to be able to get these frequencies back so we can decode the message. So we'll go ahead and run our signal. I also wanted to say that the baud rate needs to stay below the carrier frequency. So if it gets as it gets closer to the same value as the carrier frequency, then you start to have mismatch bits running into the ASCII problems. We're not getting the correct characters out. So let's go ahead and run this script. Alright, we've just saved our waveform file, and we've got our baud rate back at 490. I'm going to take this wave file and save it to my phone.
And now we'll go ahead and play back our message and record it to MATLAB. Well, that's the best we're going to get. It's sort of started decoding some stuff. Been having a lot of issues with my laptop. It's running pretty hot and the fan's on all the time, so it's got a lot of background noise from that. But I'll run it again with a quieter signal, and we'll see what we get out of that. Try this. Yeah, we got a lot less out of that. Try one more time a little bit louder. We got a little bit back out of that. Alright, let's go quieter and we'll see what we get. Did it overload it? Oh, I don't know why I skipped on that one. Alright, we'll try one more time. Maybe not. Well, yeah, we don't have any version of my name at all in there. At least we got a signal out of it. Well, that's the function set, the TSK transmission. does the modulation. It takes our waveform and changes it from that ASCII character value to a set of binary bits, and then does that framing with the keys one on each side, and then we modulate the signal and then save it to our write file. And then when we do the demodulation, I run it through a bandpass filter. So we first get the waveform file, and I run it through a bandpass filter. I set it to be 1.5 above 1.5 times our baud rate. That way it gives us a little bit more room on the sides. Not a lot, but a little bit more. And this elliptical filter worked really well to filter out that signal. And then do the absolute value. We do a low pass filter, and then we take away the DC offset. Then we go through the process of finding where all those frames are at, and then trying to make sure that we match them up so we don't have any false positives. As you can see, it didn't work that well with the audio signal here. It works great when I'm not trying to transmit it through the air. It works perfectly every time, but like I said, my computer is making a lot of sounds and stuff, and it's definitely picking up on the mic. It's been really hard to isolate that. But either way, and then it goes through time difference to make sure that those values are exactly that 8 modulus away. Modulus using 8 to make sure that it's a factor of 8. So we're getting through all the characters. And then it goes through and decodes the message, puts the message pieces in an array all of themselves, and then changes them back from a polar to binary, and then we take that binary, change it back into character. All right, thank you very much.